All right, since you were dying to know about this next part here, t distributions. Just like before, we had this thing called a z distribution, or aka this was our normal curve friend. We used z-scores to make that up, right? So it's like a z distribution. It was nice. It had our 3 tick marks away. It was bell-shaped. It was whatever. It was beautiful. And the nice part is we could literally use this for anything, and it's the same across the board. Well, lo and behold, there's other things besides z distributions. There is this little sucker right here called a t distribution. New stuff, okay? T distributions are a smidgen different. So let's look at the differences here. All right, so when we had a standardized normal or z distribution, aka the normal one right here, there was just one distribution, one curve that we draw for everything. But when we have a t distribution, there is an infinite. I don't think I spelled that right, but you get the point. There is an infinite number of t distributions. Here, I'll put an infinity sign, okay? T distributions are similar. They're very, very similar. They are still single peaked. Single peak. They are symmetric. And they are bell-shaped. So if I was just going off this right now, you'd be like, dang, you're talking about the same thing. I'd be like, sorry, I'm not. Okay, the center is still 0, and the total area under the curve is still 1. Sounds very similar. Here is the kicker. But. What is different about these is t distributions have a greater spread. They're more spread out. They have less area in the middle and more area in the tails. T distributions are identified by this thing called degrees of freedom. Degrees of freedom. The freedom ring. Okay, the degrees of freedom. Thing is, you don't actually have to know what this is. Okay, we're not going to learn what it is. You do need to know how to use it, but it's not really in the extent of our curriculum. So what is the degrees of freedom? Degrees of freedom, all you have to know is this part. You're just going to take n and minus 1. That is going to be your degrees of freedom. Okay, so actually you do need to do this. So think about this. Here we have t distributions. I'm going to throw this back up here. T distributions have just more area in the curves. So if I was just to like cut this off right here, there's very little area outside here. Remember, voila, very little area. But over here now, if I cut it kind of in the same spot, there's much more area out here in this area, the sides and the tails, than there was before. And this one is more like my t distribution. Okay, so let's think about Play-Doh for a second. So I don't know if any of you have ever played with Play-Doh, but it comes out when it's brand new in this little tube, and you just squish it, and it's great. Okay, love it. We're gonna kind of think about that idea for a moment. Maybe that'll help you. So when we have degrees of freedom, if we have a low amount of degrees of freedom, okay, think about taking your original, what you had as your OG original normal curve. It looks really bad. And think about squishing it. Why is it? Think about squishing it down like the Play-Doh. And now it becomes something more like that. Right? So where you cut it before, there was, some area, but now if I cut it in the same spot, there is a lot more area out in the edges. So lower degrees of freedom, think about squishing it. And now we have more area out here. Okay, so this becomes more t distribution like. I don't really know how to word it, but it's becoming more like a t distribution with lower degrees of freedom. Versus if you have a high degree of freedom, think about that as you have some curve, and you are going to take that curve, whatever it was before. Okay, maybe there's the original one. And what you're going to do with that curve is you're going to take it and you're going to pull it up, because you only have the same amount of area. So now when you pull it up, you have something that looks like that. And so you started with something here, and now in the same exact lines, I mean, I drew that so crappy that you can't even see what I'm talking about. Let me redraw that. Okay, so, oh, it's pink, sugar. OMG Zols. Oh, sorry. Forgot I'm like recording myself. Okay, so there's my curve. It's still really bad. Think about it this time. We're going to take it and we're going to pull that up. So now, when I pull it up, oh my gosh, Haley, it looks something like that. Still really bad. So if this was the cutoff for the area the first time, I mean, it's not lined up at all. It still looks equally bad. I don't know how to make it look pretty. But think about it. This time, you should have less area in the tails. So think about this picture. This picture is way better. So when the degrees of freedom went down, we got more area in tails. Versus when the degrees of freedom go up, we should have less area. Just really zone in on this picture, okay? This one looks beautiful. That one's making it, okay? Less area in the tails. This one, when you have less area in the tails, you're becoming more like a normal distribution or a Z distribution. So more degrees of freedom is good because it's becoming more normal. Okay, so if we come back over here, it says, as the degrees of freedom increases, the T distribution becomes less variable and more like a standard normal Z distribution. Okay, so thing to note here, and that's what I was just trying to talk about here. Degrees of freedom goes up, it pulls it up, the area and the edges get smaller. Okay, so this is so ugly, and this is why we don't really work with T distributions that much. That's the formula for a T distribution. Ugly, we're not working with that. I've just ignore these pictures for right now. We're going to focus in on these ones, though. So here is your normal curve, right? And here is your T distribution over here. If you look, this is where your Z-score was, right? Z-score right there, and your Z-score would be right there, cutting it off. Over here, now we don't have Z-scores. We have these things called critical values. So this would be like my T-star and my T-star. Critical value, right? If you notice, they're both in the same spot. They both have this is a Z-score of 2, right? And this is a T-star of 2. Which one looks like it has more area in the edges? This dude's definitely got more area out here on the side. Okay? So with that being said, the smaller the n is, the more of a problem this is. And look up here. The smaller that my n was, the more that these were off from each other, right? This has a bigger difference than this one, right? Okay, so the smaller n is, the more of a problem we have. The larger T-star needs to be. So think about T-star. T-star will have to get bigger. This will have to go out farther to correct more, right? Think about this as a correcting. The more of a problem this is, the more we're going to have to correct. This is like our correction. Okay? And the larger T-star is, the fewer degrees of freedom we must use. So think about, I'll put this out here. So if this is my t distribution here for a second, this little guy, if we focus on this one, it says the smaller n is, the more we'll have to correct. The fewer the degrees of freedom will be. The fewer that, whenever we have smaller degrees of freedom means that we're going to be more and more like a t distribution. The more and more we're going to have to correct, the more it'll look like this. Smaller means a larger t star and fewer degrees of freedom. And again, think about, how did you find the degrees of freedom? If this is small, that's going to be pretty small. All right, so we'll go more into detail. Hopefully this was helpful. It's definitely new stuff, but you guys got it. Keep your head up. See you guys.